Hello. So we're going to continue with what we were discussing last time, but today we're going to focus on still on Schwarzschild space-time, and we will try to address the question of what is mass. If you remember well in the last lecture, I was mentioning that how can it be possible that you have curvature if you don't have mass? Because remember the Schwarzschild solution corresponds to the solution. This is a solution of the Einstein's equations without with a source term, without mass. So for me, at least, at the beginning, this was extremely confusing because curvature, in my mind, is linked to mass, and mass is linked to curvature. And since I assume that this will be the same for some of you, I have tried at least I have tried to prepare a possible explanation that well, I have two explanations. One is a usual, a pragmatic one, and the second one is the rigorous one, which I don't expect you to fully understand by now because I have not given you yet the background that you need to understand it. But with time, probably we will get into the details. That would be my wish, my personal wish, that we get into the details of it. Okay, so we have here our usual space-time, this conformal diagram. I'm going to start using standard notation, so to say standard, because this will be useful for you in the future. So, as you can imagine, this is the spacetime corresponding to the two universes. I have these two lines over here. This is, if you remember well, this is space like infinity, which we are going to call I0, and the same over here, right? I0. This is a time like future infinity, which we're going to call I plus, referring to the future, and here we have I minus, referring to the past, and over here the same, I minus, I plus. For the surfaces, we will use capital I's. So this is I plus, this is a null surface, a null infinity surface in the future and in the past, and the same here, plus and minus. This is the solution corresponding to a radius of 2. Remember that I am setting G equals C equals 1. So this is as well a solution corresponding to R equals 2. And the same applies for this. R equals 2 and R equals 2. And over here we have R0 and here as well. So that these two surfaces, which you can reach in a finite time, correspond to singularities. Now, a singularity is a very fancy name for something that we don't understand. It's something singular, right? It's something special. It's something that we do not understand. So we could actually call them I don't have any idea here or whatever. So when we say singularity, what we are meaning could be this word here. I don't have any idea of what is going on here. Okay. Now we have talked about the black hole and over here of the white hole, so that things from this universe can reach us by crossing this event horizon or this other universe, with the only condition that it does not travel faster than the speed of light. Now, consider the following. Consider an observer here, somebody who's going to fall into the black hole, and in this other universe, another observer. Can you think of a way for this observer to come in contact with its observer here, to exchange information? Imagine that the left one has a book, and this is the left one, and the right one wants that book. So how would the left observer give information, give that book to the right observer? I'm going to pause the video now for a few seconds, on my side, and then you can pause the video on your side. So I'm going to pause the video on my side to clean the blackboard, but you can pause the video on your side to think about it. So how would the left observer exchange information with the right observer? The only condition is that you cannot, travel faster than the speed of light. So think about it. Okay, I hope that you have thought about that, and I'm going to give you now the solution. So for an observer traveling, because time is flowing this direction, this does not have any kind of meaning in the conformal diagram. Of course, this is just giving you the arrow of time, the flow of time. And that you cannot travel faster than light, so that you cannot go like this. You must move, remember, as usual, inside of a light cone. Any event must have a future and a past light cone. So an observer here has information who wants to pass over to that observer on the right, left universe. So the only possibility of exchanging information would be when they both cross the event horizon of these two different universes. Starting from these two different universes. So this region here, the inside of the black hole, is the only place in all of this diagram where they can exchange information, shake hands, say hello, before geometry around them squeezes them to death. And since we're talking about this, let me mention a couple of interesting things that happen when you cross the event horizon of a Schwarzschild black hole. And I mention Schwarzschild black hole because when we will go to CARE, things will be much more different. This singularity, I don't know what this is. This is a very nice singularity. We like this kind of singularities because they are space-like singularities. And we can predict the wall line, so all of this trajectory, orbit, whatever you want to call it, from the beginning of it down to the singularity, all the time, all the way, if your black hole is Schwarzschild. Schwarzschild. When we go to CARE, things are different and much more complex. In particular, you cannot predict for a given surface onwards, upwards, or whatever you want to call it. You cannot predict what is going to happen to the trajectory, and that makes things much more unpleasant. So let's go. Let me think a little bit. Yes, I'm going to delete this. So let's imagine now, again, this is the singularity. I don't know what this is. I don't know what happens beyond here. When I say I don't know what this is, it is not true. What I mean is that from that point onwards, it does not make sense with the mathematical and physical tools or knowledge that we have nowadays. We don't have any idea of what happens beyond that point. So it does not make sense to ask what happens beyond that point. And I'm going to make this sounds very strange, but we have a very similar case in electromagnetism, and I will talk about this in a few minutes. But let me mention before that, let me mention the following. So we imagine that we have this black hole over here. So this black hole here corresponds to a black hole with a mass of, I don't know, let's say 10 to the 10 solar masses, okay? Because if it was a very small black hole, then we would be totally disrupted before getting, before crossing the event horizon. Now, let me delete this, not this one, but this one here. So, if you cross the event horizon, at first, you will not notice anything. Because if you remember, lines of a constant volume, if you want, oh, this is I'm deleting, sorry about that. So lines of constant radii look like this, okay? So at this point, if you are located at that point and you look around you, all of the universe looks the same. You have the same volume. You are in an isotropic universe. Regardless in what direction you look around you, you see the same thing. But let's go back to what I wanted to mention. If you have a black hole of 10 to the 10 solar masses, it's going to take you, so a human being, something like, probably 10 to the 4 seconds. Okay, maybe I'm wrong. I have to check that. 10 to the 4 seconds to reach the singularity from the moment in which you have crossed the event horizon. So all of that is going to take you 10 to the 4 seconds. Now, when you are exactly at the surface of a 2, you are fine, because the tidal forces are very weak, but soon things will become very unpleasant for you. During those 10 to the 4 seconds that you have of life, you will experience tidal forces increasing. So geometry around you, and actually not around you because you are in that spacetime, so everything, the geometry, will start increasing to the point that, so it will start squeezing you, the curvature will increase until the point in which you are torn apart. So geometry contracts. Now, an interesting experiment and an interesting calculation that you can do is that if you were followed by another observer falling into the same black hole but a little bit later than you, like for instance this one, the proper distance, so distance between you and the other observer, can you guess what is going to happen as you approach the singularity? Now, if you look at the usual thing, so this is Earth, this is the center of Earth, and you have somebody falling here, and you have somebody falling over there. Okay, so as they fall, they they tend. This is the trajectory that they are following towards the center of the Earth. So the initial distance will become, smaller and smaller and smaller until both of you hit ground. Now, in general relativity, as usual, things are different, because when you get closer and closer to the singularity, the distance between the two infallen observers is not going to be smaller. The distance will not be kept. It will be increasing over time. You can calculate this proper distance by looking at the deviation of the geodesic. And it is expanding, not shrinking over time. So that's the fun thing. The proper distance between the two of you is going to be expanding over time. Now, let's try to understand what would happen to one of these observers when this person crossed the event horizon. So imagine that somebody crosses the event horizon like this, and this person, for some reason, realizes that this is the right observer, and I think it was a boy with skirts. I don't know. So it is a he. So this person crosses the event horizon, and for some reason, he realizes that he has done so because there is no way he's going to find out. But let's assume that this person realizes that he has crossed the event horizon. Maybe he's starting to notice some unpleasant squeezing of his body, and he realizes, oh, well, looks like I've crossed an event horizon. I would like to go back. Well, there is no going back, first of all, because to go back, you can only go back in space. You cannot go back in time. But if you, for some reason, because you know that you are going to die, and you are just panicking, and you do silly things, which is what people do when they know that their life is in danger. This person goes back to the assumption that the world is like it is in an eternal way, so he can go back in some way. And then he decides to accelerate. He has some powerful rockets attached to his back, and he decides that he wants to go back because he's trying to do this. Okay, so what is going to happen to that person? You might want to pause the video now to think about it, and I will give the solution in 3, 2, 1, 0. So this person, if he had this silly idea of accelerating and trying to reach the past event horizon in a special way, could say it doesn't make sense because it's like trying to reach the Big Bang by flying back to the past. Does not make sense, but anyway. So this person tries to go back before reaching the singularity and accelerates. If you accelerate, what you do is to get closer to one of these slopes of 45 degrees. So if you let me delete this. This is a zoom in. So if you try to accelerate, what you do is that instead of following this trajectory, you start to, get closer and closer to one of these slopes, to one of these sides of 45 degrees. And you can calculate, and this is probably a useful exercise for you, you can calculate what is going to happen to the person, but you can actually see that already with the light cone that I just drew. By accelerating your motion, you are going to only shorten your life. And this is so because your proper time will decrease, which will not help you to, delay death, but quite the contrary. So if you ever, for whatever reason, fall into a black hole, please stay completely quiet. Don't move. Don't make a sound. Don't move a little, not even a finger, and enjoy the travel until you get to the singularity. Because by not moving, by following your wall line without trying to accelerate on it, you're going to maximize your proper time. The slower the move, the farther away from the slope, the more time you will live. Sorry, I meant that you will live. And let's go back to the usual diagram. Remember that this is I naught, and this as well. I plus, I minus, I minus, I minus, capital I minus, capital I plus. There you go. So over here, surfaces of constant radii look like this, if you remember well, like this. And when you cross the event horizon, then you get this, which is what we discussed last time. Now, I told you that when we are inside of this region here, when you cross the event horizon and you're in the black hole, you see isotropy. I'm going to make a zoom in of this figure. Here we are. So these are lines for, I don't know, say 1.7, 1.4, 1, etc. until you get to r equals 0. Now, I told you that if you are on one of these surfaces, you see isotropy around you. And and I also told you that when you move, when an observer crosses this line, the event horizon, and gets to the event to the singularity, that observer is going to be it's going to be entirely torn apart at some point. So ask yourself the following question: how is it possible that you have tidal forces if your universe is isotropic? So anything moving in the interior must cross those surfaces of constant radius. So they describe the entire interior at a given time, and they are isotropic. But there is nothing special there. The curvature is finite, which is why you will not feel anything special when you cross the event horizon. So if by some cause you cross the event horizon, you would not notice anything. Only that everything around you would look the same. Everything is regular up to the singularity, which is the end of time. So going back to that question, how can you have tidal forces if you have isotropy? So the point is that you only have isotropy on those particular surfaces, like this one. Now, if you move away from those surfaces, you can have asymmetries. So if you have directions, if you have you move away from that surface in some direction, you're going to fall, you're going to feel tidal forces, which will squeeze and stretch you. Unless you are a perfect point particle, and we know that human beings are not point particles, they look like this. This is a physicist's first approximation to a human being. I will leave the details to the engineers. That person is going to feel tidal forces because some parts of your body will be closer to R0 than other parts of your body. So I cannot repeat this enough times. The interior of the black hole is not stationary. It is rapidly evolving. Thinking of spherical symmetry is misleading. The other thing, which is a consequence of what I just said, is that there is no singularity at the center, because there is no center. And we can calculate this by calculating the Killing vector fields. Remember that a Killing vector field is a vector field on a Riemannian manifold or a pseudo-Riemannian manifold that preserves the metric. So these fields are infinitesimal generators of isometries. This can also be expressed by saying that the flows of these fields are continuous isometries of the manifold, and that flow generates a symmetry. Moving each point on an object the same distance in the direction of the Killing vector field will not distort distances of the object, which is why it makes things so interesting. So what is if you're wondering about all of this, we can actually look at an exercise which I proposed based on a question that a Chinese student asked me. She asked me whether there is a connection between Noether's theorem and these flows of the Killing vector fields inside of the black hole, because that's something very interesting that could help you into understanding what is going on inside of the black hole. Let me check at notes so that I remember what I wanted to say. Okay. Yeah. So outside of the black hole, we have three space-like Killing vectors that generate rotations. Inside of the black hole, on the contrary to the exterior, there is no time-like Killing vector field, so that there is nothing that is stationary. But outside, spacetime is symmetric. So this is why it looks like, well, it is spherically symmetric and everything is fine. It is as we know it. Now, let me go back to what I was saying before about the singularity and this so that you get an understanding or an intuition of why we don't know what happens over there. I'm going to start the blackboard. So when you think about this from the point of view of electromagnetism, we have a very similar situation. Imagine that you have a point particle Q with a charge which is different than 0. Well, we know that we can describe the electric field everywhere in space-time, but for a point. So you can describe the electric field everywhere in your space-time, but for a point. And what is that point? Well, that point is the charge itself. Why is that? Well, that's because the field depends on Q divided by the distance to the square. So that if this is your charge, and you're getting closer and closer to the charge, the radius is tending to 0. So that here, this thing is tending to 0. And you have a problem. You have something divided by 0. The theory breaks down there. You might also remember that I said, and this is connected to probably the most important part of this class, that when we draw the conformal diagram like we had done before, we were assuming that the black hole had been there forever. So look at this diagram. When I draw this line over here, what I am doing is to assume that the black hole has existed forever, because this is an infinite time-like point in the past, and this is its counterpart in the future. So by drawing that line, what I am assuming is that the black hole has existed forever. Now, we will talk about this in the next lectures, I think, by looking at the collapse of a star and the formation of the black hole. But if you are wondering, in some sense, what I do is to envisage the Schwarzschild solution as the limit point, or maybe, if you want, the final equilibrium point of a much more general solution, one that begins, let's say, with that spherical distribution of matter that collapses and forms the singularity. Because what I asked in the last lecture, sorry, that was a mistake in the last lecture. So how is it possible that you have curvature if you don't have mass? Because we're talking about vacuum. How can you have curvature? The question actually is, what happens to the matter? You can think of a star, like our sun, as a collection of point particles or spheres of matter like this. And this is, by the way, how astrophysicists simulate in supercomputers, for instance, the evolution of a star. They start with some initial conditions given by a polytrope. If you're talking about our sun, polytrope. In the case of our sun, the polytrope has an index of 3, which means that you distribute this matter. You have an analytic solution in equilibrium for the star, and then you let it evolve. You can also do that at least partially analytically by looking at the length and equations. But in any case, so you have a star which is made up of these particles. So each one of these particles, when, given some conditions, because not all stars will follow this evolution, will have this doom or fate, given some conditions, and I will mention which ones, because the important thing is that we're not only talking about conformal diagrams here, we're talking a little bit about general relativity, some mathematics, but you also have to know astrophysics to understand the whole thing. For a given set of conditions, one star of a given mass and metallicity will collapse and form a black hole, which means that one particle here will get closer and closer to the center because the two competing forces of phenomena, of processes in the star, which are the pressure and gravity, are not in equilibrium anymore, and the one dominating is gravity, so that the star cannot support, endure its own mass or weight, because it is in its own gravitational field, and it's going to collapse towards the center. So these particles, all of them, will move towards the center, and they will make something very, very, very compact that eventually will form an event horizon, and so that you will have a singularity. Because if you have an event horizon, you have a singularity, and that was Penrose who demonstrated it in the first place. So you can understand that each one of these particles has its own trajectory, which means that we can locate them in the conformal diagram. Each of these particles is going to move in a given way in the conformal diagram. But the important thing is that at some point, those particles, all of them, will reach the singularity, and they will vanish. So the question then is truly, what happens to the matter? Because the process of forming as a singularity does not include a process of producing that the limit of this tensor mu nu equals 0. Another thing to take into account is that the spatial solution per se is vacuum, and then T mu nu equals 0 and has no curvature, which mathematically speaking can be written like this. For our specific case, what we mean is that at least the four-dimensional space-time has no Ricci local curvature, which is what we directly associate with mass. However, it has a Weyl, distant and tidal curvature, as well as Gaussian. Local in the three-dimensional spatial slices. And this is where this illusion of matter comes about. So now you can ask yourself, okay, well then how can I calculate the mass of a black hole? if I am completely confused, and that's completely normal because I have not given you the mathematical tools. We have not done a single mathematical operation until now, and I don't expect you to, by some good gracious miracle to understand all of this. But you have to ask yourself, how can you calculate the mass of a black hole? So how do people calculate the mass of the black hole at the center of our Milky Way? You know that in 2020, right, the Nobel Prize was awarded to the discovery of a supermassive dark object at the center of our Milky Way, of our galaxy, along with the calculations that Roger Penrose did. So these two astronomers, one in Germany, Genzel, who is a good friend of mine, and Andrea Getz in the US, they estimated the mass of something which is extremely compact. It is confined in a radius of, if I'm not wrong, 22 millions of kilometers, which is tiny from the point of view of a galaxy, and it has a mass of about 4 million of solar masses. While there are still some possible candidates, like say boson stars, etc., it is very likely that it is a supermassive black hole. So, in any case, how did these people estimate the mass of that black hole? Well, if you are at the exterior of the black hole and you want to be pragmatic, and you have to be pragmatic, because this is the danger of the beauty of mathematical calculations and general relativity, that you can get absorbed by it and lose track of reality. And I have seen many people falling into this trap by doing extremely complicated but somewhat useless operations. But this is my personal opinion. Of course, I don't mean any kind of offense to anyone. I have a lot of respect for my colleagues, but sometimes I wonder, why are you doing that calculation? My impression, and I might be completely wrong, is that they are doing it because it is fun to do it. But we are trying to solve a problem here. So you have to keep your feet on the ground, okay? And so how do you determine the mass of the black hole? Well, if you're outside of the black hole, and you have understood what I have said about flows of the Killing vector fields, etc., you have spherical symmetry, everything is wonderful. So you run a Newtonian experiment, or something very close to a Newtonian experiment, and maybe you need some mild relativistic corrections until you determine the mass of the black hole. It's very easy. Well, it's not very easy. It has taken us like 2 decades to get a very good estimate of the mass of the supermassive black hole, and actually to get 2 orbits of a given star, which is called S2, on the side of the ocean, and in the New World, in America, it's called SO2. I mean the continent, not the country. Although the country was, of course, was the United States of America. So we have one star, S2 or SO2, which has described 2 orbits around the supermassive black hole. And guess what? They have managed, doing extremely complex, because these observations are extremely complex observations, they have managed to see the periapsis shift, which is wonderful. In a recent paper by Genzel, Vitor Cardoso, and many of their collaborators. I just remember these 2 names because I know them personally very well. So, what I was saying? So, this is the way you calculate the mass of the black hole. You run Hamiltonian experiment. You do not need a full general relativity to do that. Now, the other question is, how do you formally implement or derive the mass, the concept of mass, when you are looking at conformal diagrams? And this is what I want to talk about now. So for that, we're going to use the so-called ADM formalism, and it's called like this because it's been named after the three people who developed it. Arnowit, actually I'm not sure how to pronounce it, Teaser, I mean, I don't know where he comes from, and Misna. So ADM. Okay. So this is a formalism in which you present the formulation of general relativity, and it is the standard, or it's the canonical way of looking into quantum gravity and numerical relativity, and it goes back to the 50s, I believe, or the beginning of the 60s. So it's a Hamiltonian formulation of general relativity. Okay. So in this formalism, you suppose that space-time is foliated. You have a sequence of leaves, as they call them, which represent space-time. These surfaces are called sigma at different t's. So this could be t1, t2, t3, etc. And the coordinates of each slice are given by x, y. Now, we use the metric tensor of three-dimensional spatial slices to derive or to reassign them the dynamical variables. So we use gamma ij of txk and their conjugate momenta pi, as you say in English. This should actually be called p in ancient Greek, because ancient Greek had tones like Chinese. Txk. So using these variables, you can then define a Hamiltonian. And if you have a Hamiltonian, you have everything. You can write equations of motion. So this is the basic idea of this ADM formulation. So the way to calculate this mass is via Cauchy surface. I will explain what this is now by going to the blackboard again. And so this is the usual thing that we have talked about many times already. And so we need to integrate along a spatial hypersurface, or a Cauchy surface, if you want. I'll write it here. Spatial hypersurface. From this I0 to this I0. Okay, so this would look like this, something like this, something similar to this. And this is so because what we are implicitly doing here is to foliate, as I mentioned before, spacetime in a sequence of spatial hypersurfaces. Each of these hypersurfaces represents a moment in time. Like, for instance, you could have many of them, right? I'm going to draw a few of them, like this one, and this one, this one, this one, this one, etc. The flow of time, as usual, is in this direction. This is the flow of time. And it is important that you do not get confused about these lines, because well, the first thing that popped up in my mind when I saw this is that how can you do this? You are breaking causality, and what's even worse, you're moving from one universe to the next universe. But this is just a misconception. Consider the usual spacetime diagram, and this light cone over here, as usual, and I have said this quite a few times. As long as you are instead of a light cone, you're fine. But this does not prevent you to define any other curve in this diagram. So, for instance, I don't know, consider this vector here. It does not represent physical motion. It is not causal, but there is nothing that forbids you to consider that vector in this plane of space and time. In the same fashion, we can consider those hypersurfaces, and for that, so once we have clarified this, let's go back to the first figure, and you have to remember what a Lorentzian manifold is. So, Lorentzian manifold is a particular case of a pseudo-Riemannian manifold. Manifold, in which the signature of the metric is, well, depending on the sign convention that you're using, is 1 n minus 1, or it could be, n minus 1, 1. So these metrics are Lorentzian metrics, and of course, well, this is this kind of metric was named after Hendrik Lorentz. And a Cauchy surface is a particular type of submanifold of a Lorentzian manifold, which is very commonly used in general relativity. So you can regard it as an instant of time, and they are very important, as we have seen before. For instance, in this ADM formulation of general relativity, they are important because they allow you to formulate Einstein equations as an evolutionary problem. So if you want to be a little bit more formal, let's consider the following. So consider a Lorentzian manifold given by M and G. We say that a map, let's say for instance phi, or again in ancient Greek pi. I insist on this because I am a fanatic of the ancient Greek culture. In any case, let's stick to English. So phi is going to be a map between, say, A and B and M. So this map is an inextendible, differentiable time-like curve, in the Lorentzian manifold if 1. It is differentiable. 2. Phi prime of t is time-like for every t in the interval a, b, and 3. Phi of t does not approach a limit as t, is increasing to b or is decreasing to a, which I don't know how to write. Sorry. Okay. So let's say as t increases to b or as t decreases to a. So a subset S of M is called a Cauchy surface, Cauchy, French, if every inextendible curve in your Lorentzian manifold has exactly 1 point of intersection with S. So to go back to this diagram, so these curves, these slices, these hypersurfaces over here, do not represent the trajectory of anything which is physical, because in order to move along one of those surfaces, for instance along this line here, you immediately see that you would have to move faster than the speed of light, but you cannot do that, as we know. You can only move on a light cone, remember. Okay? So again, don't get confused about causality. It's not that we are joining different universes, because these spatial slices don't represent anything which is moving, nothing physical. It's just a special cut of a space-time. And we are covering the whole space-time. So from this I0 to this I01 in a kind of say fictive way, because we are assuming that the black hole was not created, it was present forever. Remember that this corresponds to I minus, and this corresponds to I plus, and we have discussed this already. So I hope this is clear now, because this is a question that I was confused myself at the beginning, but I also got some questions by students. The problem is that you cannot go from one universe, from the left universe into the right universe. You can only meet inside of the black hole, which is this area here. So two observers, as we said before, from the left and right universe can meet, but they can do only meet inside of the black hole. So we're doing all of this because we're trying to find a formal way to define what is the mass of the black hole. This is the black hole, of course. But the problem is that mass and energy are very subtle concepts in relativity, because you can define them in a given certain situation, but not in all situations, because we do not have a local definition of energy. However, if you have a symmetry in the system, and this is why you need to know differential geometry, differential topology. If you have a symmetry, either local or asymptotical, as it is our case, then you can define a concept of, say, mass. The most common one, or one of the most common ones, is the ADM mass, which profits from the asymptotical flatness of a space-time. You know that over these surfaces here, with capital I's, well, actually should be like a curly I's, but just use capital I's. Space-time is flat. Space-time becomes more flat as you move out. In the when I say out, I mean the direction of those rays of light. My goodness, that I was mentioning, I think, in the first video. So in this case, we can define an integral. So, and we're going to define that mass. So consider a space with a 3-manifold M and flat positive definite 3-metric G, like this. In this case, and as I have explained before, you can define a concept for mass, which is the ADM mass, by evaluating this integral. The mass, this is not the manifold, this is the mass, equals 1 divided by 16 pi. In the limit, this is the limit for me, in which a topological two-sphere S tends to that I0 of the integral over the topological two-sphere S of G mu nu multiplying G mu whatever beta nu minus, let's just draw two signs so that you know what line is the line that we're on. G mu nu, right, beta n alpha ds. Now, of course, since S is a topological to a sphere, ds is the area element, and this one here is the unit normal pointing outwards. Now, it is interesting to note that in this formulation, this integrand, so the integrand over here is not in covariant form, not in covariant form. And this means that our definition of m, of the mass, does only make sense for a certain class of coordinate system, which we call asymptotic Euclidean coordinates. Asymptotic Euclidean coordinates. In such a system, the metric components are actually required to be of the form G mu nu equals to delta mu nu plus order of 1 over r. It is important to note that you can prove that the integral does not depend on the slice that you choose. So you could use this one, or you could use the following one, or this one here. It is a conserved quantity, which is why it makes sense to use it as the total mass of space-time. And pay attention to what I just said, the total mass of space-time. Since we are in vacuum, by integrating from the left I0 to the right I0, we are calculating the total mass of our space-time, which is empty, but for the presence of the black hole. So that de facto, what we're doing is to derive a conserved quantity which we might envisage as the mass of the black hole. Now, by using the Klein-Gauss theorem, you can convert that volume integral along one of these hypersurfaces, like this one, for instance, into an integral on the surface at infinity. You can convert the volume integral, yes, into an integral on the surface at infinity on a sphere over there at infinity, which is I0. Because remember that we're using spherical coordinates. We are talking about r, so that a point represents a sphere, and over there at I0 we have a sphere. So by using the Klein-Gauss theorem, you convert that volume integral into a surface integral on a sphere which is located at infinity. Another typical question that I have got quite often is that why between those two I knots? So we have our typical conformal diagram in the spatial solution here, right? Sorry about that, I'm getting a lot of notifications. And this is one I naught, and this is the other I0 or I naught, whatever you want to call it. But I'm telling you that we have to integrate over one of these Cauchy surfaces. So since in principle, not in principle, since we were talking first about this right universe, this left universe, etc. The question that I have got is why cannot extend this to further universes, black holes, etc., something like this, right? So that why would we have to consider only the integral along one of these hypersurfaces and not say between this potential I naught over there and this one here? And the answer is that this is not possible. In Schwarzschild spacetime, what we have here is all that there is. You cannot go beyond the singularity because this is the end of time, of actually space-time, and you cannot go further than the null infinity I plus and I minus surfaces. This would be actually the other way around, like this, because they are already infinity. So what you are seeing here is all that there is. It's a whole space-time. And well, I think that this is enough for today. And I'm going to finish this lecture or summary by stating a question that I got from a very quite smart Chinese student. So she asked me whether it would be possible to make a link between Noether's theorem in physics and the fact that inside of a black hole we have these killing beta fields. So can you somehow relate those flows with Noether's theorem and try to derive something interesting, like say conserved quantities? I'm going to leave it here as a kind of question for yourself if you want to work out the problem, which I assign to the students actually, and I will provide you with the solution in the next video. Thank you, and bye.